All right, the purpose of this video is to try and demonstrate the photoelectric effect. The demonstration is going to look a little bit different, and hold on, let me see if that focus gets in there. Let me hit the autofocus real quick. Low light level. I might have to turn on the light for a second, hold on. All right, so if you're wanting to have your book open, go to page 69 of volume 5. And I'm going to talk about some of this information in a minute, but first I want to give you just a visual of how I'm going to demonstrate this. This device is called an electroscope. And inside of here, in the very middle part in here, protected from the wind by these pieces of glass, are two small sheets of metal. I'm going to call those the leaves of the electroscope, like leaves on a tree. Now up top here, I'm able to basically touch a charged object to it, and that will affect the leaves. And you can even see it there kind of moving just a little more on that in a minute. At the very top here, you can see that I've attached to this, I'm going to tilt this so you can see it, a piece of zinc. So this kind of weird oval looking shape is a piece of zinc. The shape of that is actually rather important, as I'll discuss in a minute, all right, and we'll come back to this. But so we've got the leaves of the electroscope and this piece of zinc up here, and then I'm going to shine some UV light on it in a minute. Let's go back to the board so you can see some of the information that we need to know. Okay, fact number 1, if you rub plastic with fur, the plastic becomes negatively charged. So you get a bunch of electrons on this piece of black plastic here. So I'm going to rub this with fur in a minute, and this will become negatively charged. Okay? However, if you take a piece of glass, maybe you can see that there, and rub this with silk, it becomes positively charged, right? And so just in case you're curious here, the plastic becomes negatively charged because the fur donates electrons to it, to the plastic. And here, the glass becomes positively charged because the silk will strip electrons off of the glass. So there's a different bit of physics going on there. All right, next, charge tends to accumulate at sharp points. I wanted to mention this because I had trouble doing this demo. When I first just cut a rectangular slab of zinc, all the charge would accrue on the corners of the rectangular slab of zinc. I'm like, oh. So if we want the charge to accumulate in the leaves of the electroscope, we need to have a nice smooth piece of zinc, something that's circular or oval, basically something without sharp corners. That's important. All right, next, our light source has a long wave UV, meaning long wavelength, and that wavelength is 365 according to the manufacturer. Our short wave UV in the same lamp we could choose is lambda equals 254 nanometers. And I looked up some numbers for zinc, and there's a bunch of different numbers you'll see on the internet, but there's a basically a cutoff wavelength for the photoelectric effect to work. Wavelengths have to be shorter than this cutoff wavelength, and so let's just call this about 288. All right, so let's just cheat and kind of pick something in the middle there. Let's say it's about 288. It depends in the literature which resource you use. All right. And so this corresponds to about 4.3 eV if you're curious. But as the wavelength gets shorter, the energy of the photon is given by hc over the wavelength. So if the wavelength gets shorter, it has more energy, and basically short wavelength or high energy photons are able to kick electrons off a piece of zinc, as long as the energy of those photons is greater than 4.3 eV or so, depending on the resource you read. One was like 4.25, another was 4.33. Okay, so, and then one last note, while it's possibly unnecessary, actually two last notes. I wore gloves while I was prepping this experiment just so that oils from my hands didn't get all over the electroscope, which caused charge to bleed in weird spots. And then another thing, notice this here. I recently sanded the piece of zinc just so that there's no oxide, or how about I just say grime. There could be grime on there, dirt, it could be an oxide, whatever it is. So yeah, I don't know exactly what was on the piece of zinc, but if you don't have a fairly clean piece of zinc, this might not work. So, and then notice I sanded it. I read a note somewhere that you don't want to use steel wool because steel wool will sometimes have some oils in it to keep it from rusting, and so that will defeat the purpose. You'll get oils on there, and then that screws up the experiment sometimes. All right, so, okay, plastic will have negative charge, glass is positively charged, shortwave is below the cutoff, so it should be more energetic, right? Blue is more energetic than red, and obviously these are both ultraviolet, but the long wave should not be able to eject electrons. Let's go to the demonstration now, and I may have to hit the lights really quick while this is moving, just so you can see things better. I'll explain why in a sec. Now, if I just point this source at the camera, I don't think you'll see any light when I turn it on. And you don't see any light. So what this paper is for, let me turn these off again. If you look down here on this paper that's in front, maybe I'll just do this, fold it a little bit. Hopefully what you can see is when I turn this on, you can tell on the paper if the light is on or off. Now you're not going to be able to tell. That was long wave here, short wave here. Oops, did I turn it on? I didn't turn it on. There's the short wave. It's kind of hard to tell the difference on the paper that's sitting in front here, and I don't want to dose myself with a bunch of UV, so nobody's in the classroom here. Long wave, short wave, you really can't tell the difference, so you're just going to have to trust me. Short wave is this button, long wave is this button. I don't know if you can see that on the screen, but okay, great. So short wave is left. All right, so now what I'm going to try to do, charge up the electroscope. Maybe you can hear that crackling. I'm not trying to be sneaky here. I can hear it crackling. And now I'm going to touch this to here. Come on now. Oh my gosh, there we go. So what's happened is the plastic, this is ABS plastic, piping from just hardware store, okay? It's negatively charged by rubbing, so it became negatively charged because I rubbed it with the fur. When I touched it to here, some of those electrons go onto this device and they spread out. And just making sure this is a good charge. One more time. Okay, got a lot of negative charge on the leads of the electroscope. Charge tends to accumulate down there because this zinc is nice and round shaped. So I'm going to illuminate with long wave. Here we go. Let's verify that's on. It is. Nothing's happening. I'm going to turn the long wave off. Long wave is off. Short wave. Whoops. There. Short wave is on. Notice the leaves of the electroscope collapse. Hopefully you can see that. Okay, and I was probably standing in the way. Let me get a little autofocus here and then try this again. Now I'm going to turn manual focus on so I don't get in the way. Let's try this one more time. This is again with the plastic. So, okay, trying to repeat this. The electroscope is now negatively charged. You can see the leaves are spread out there a little bit. And now I'm going to come in here with long wave. Long wave. The leaves of the electroscope do not collapse. Short wave. Is that on? Come on now. There. Short wave is on. Leads of the electroscope gradually discharge. So what's happening is the high energy, short wavelength UV light hits the piece of zinc and is able to eject some of the electrons, which allows it to discharge, and the negative charges from the leaves are able to spread up here. Okay, now let's try this again, if I can figure out how to turn this thing off. Okay, and I'm going to touch this piece of metal here just to make sure it's fully discharged. I'm going to just go in here and really get it. I'm going to start this experiment over. So this is basically, I'm just grounding the system, and I'm taking any excess charge that's in there. You can see there's still a little bit of charge in there. There we go. So I find that a fast way to discharge it. Sometimes touching it to the top doesn't work very well. All right, so now in this case, now I want to take the glass rod. Oh, and that focus, always killing me. Okay. I'm going to charge up. You have to use a lot of friction here. So the plastic works a lot better. You probably noticed it's easy to get charge on a balloon, but you probably don't notice getting charge on glass as much. So now the glass is becoming positively charged. And now that positively charged glass rod is absorbing electrons from the zinc. Okay? And then that causes electrons from the leads of the electroscope to move up here, and the leads spread apart. So there's an excess positive charge down low. Now, we're going to shine the long wave on it. No discharge. No discharge. Oops. Now I'm going to get the short wave going. Short wave is live. Notice this time, no discharge. Why is that? If you want to pause the video, I'm going to tell you 3, 2, 1. Okay, remember, the photoelectric effect is about ejecting photoelectrons. Electrons are orbiting the nucleus. The protons are bound in the nucleus. And so what's happening here is, let me just do this. It's the protons can't be ejected by these energetic photons because they're trapped in the nucleus. So when I shine the shortwave on it, right, we can see that this effect only happens when the zinc is negatively charged, because the electrons could get kicked off and it could discharge. But when it's positively charged, if we try to kick off electrons, it's just going to become more positively charged, so it doesn't work. All right, so I hope that helps you visualize this photoelectric effect. I'll go back to those parameters on the screen just in case you need it. There's all that information if you need it. All right, great. Let's call that video good.